Okay, it's time to go into the last chapter here. Except we'll probably expand this because this is going swimmingly for me, I think. You guys are probably going, God, this is the most god-awful thing I've ever sat through in my life. But anyway, so let's just go ahead and go. Let's just play this from the current slide. What the reflection of light, reflection, refraction, mirrors, and lenses. All right. And we're going to look at reflection and refraction to end this chapter. Then we'll look at mirrors and lenses and human sight for the July 17 lecture. And then we'll look at the wave nature of light for the July 18th lecture. So we'll have covered some ground. We'll have done some good work here. And so let's just move on. All right, got a pulsating sphere. Boom, boom. Okay, and a sound wave. Okay, so we got a sound wave coming from a pulsating sphere. It goes out in all directions. It goes out in all these wave fronts. Now, sound waves work a little bit differently than light waves. All right, remember, electric fields can't intersect and things like that. So, but they can merge, and you can hit dead spots like in old buildings and old churches and stuff. No matter how many speakers they have set up, you can be standing somewhere and go, I can't hear a thing because it's just a dead spot. But they come out. But when we get far enough away from the spherical nature of the wave front, we'll start treating this front like a flat plane going along. See, and then eventually we get to plane fronts. And because we're looking at visible light here, wave fronts and rays, because the wavelengths are so short, almost immediately from the source, the electromagnetic wave turns into a plane front. All right, and that's the way we handle everything. Now we're coming up to my favorite equation in physics in both semesters. Here it is: law of reflection. The incident ray, refracted. I was just reading about refraction before we started. The reflected ray and the normal to the surface all lie in the same plane. Like me reading this to you? Love it? Good. And the angle of incident equals the angle of reflection. Isn't that cool? Theta I is equal to theta R. Now there's a lot going on there. So the angle of incidence for a mirror equals the angle of reflection. And that's for any surface too. That's for any surface. Even if this ray was going and hitting water, and you're going to get some reflection off, which we'll get to in a minute, but some of it's going to be refracted through. But the reflected angle will equal the incident angle. Okay, and we measure everything off the normal. All right. This is why Galileo spent so much time polishing his telescopes, because he needed that light coming in to be perfect. All right, to be nice, specular reflection. In other words, it's a very smooth surface. Here's a very rough surface, so you can see it then at each angle of incidence, the angle of incidence, so it's going off this way, and so you get a very muddy picture. All right. Images for a mirror, for a plane mirror. We're talking a plane mirror. The image has three properties. It's upright, it's the same size as you are, and the image is as far behind the mirror as you are from it. Okay? So the distance of the object is equal to the distance of the image. Okay? However, that distance of the object, guess what? That distance of the image, it's negative distance. Why? Because that is a virtual. That's a virtual image. You're not really behind there. It's not a real person behind there. That is a virtual image because no light rays are getting to it. The image is as far behind the mirror as you are in front of it. Okay? Now here you go. Because, okay, so here's what they're saying. Because the ray of light from the top of the chest piece coming into your eye, all right, it's a ray of light coming top of the chest piece, and you're looking at the chest piece in the mirror, you're seeing a virtual image, because you're not looking at the chest piece. You're looking at its image in the mirror, because it's sitting in front of the mirror. It's a virtual image, because none of the rays actually emanate from this thing. Okay? In fact, most things are reflections. All right? So it's a virtual image. Okay, the geometry used to show that the image distance is equal to whatever. Because we've got angle of incidence, angle of reflection, and for some reason our text didn't have very good problems for this. I don't know why. I don't know why they didn't have very good problems for this, but they sure as heck didn't. What is the minimum height necessary for her to see her full image? The minimum height necessary is half of the mirror. Okay, so here's her eyeballs. So we go for the top of her head, and then for her image, and this comes out to be half of her. This point DB here is equal to half her height, HF, or HM. Okay? You just need a mirror that's half your height to be able to see all of you. Here's conceptual questions I like to throw on there too. Conceptual question is, a person is sitting in front of two mirrors that intersect at a right angle. The person sees three images of herself. Why are there three? It's because of the image. Here's the image coming back. Well, she's seeing this. Boom, she's picking up this image. It's all because of angles of reflection. Okay. Here's the person looking. Boom, boom. Oh, trail this through. There's that image. Trail this through. There's that image, and she can see all three of her images. Okay, now we'll talk about index of refraction. And notice how we jumped from chapter 25 to 26. This is in the cut now. In our book, this is what, in our OpenStax books, this is what comes next. Okay, is the index of refraction, which is basically the speed of light in a vacuum divided by the speed of light in a material. The index of a material is the ratio of the speed of light. So, and things have a physical, there's a physical speed of light. The index of refraction is a physical thing for like glass, quartz, water, air, diamonds. They all have indexes of refraction. Okay? And we're going to talk about that right after we record this. So out here,